Uh, Good morning, everyone. Today we have Professor Daniel Sudarsky. Daniel Sudarsky is a senior professor at the Institute for Nuclear Science of the Universidad Nacional Autónoma de México. He is an specialist in the foundation of quantum mechanics, general relativity, and the quantum origin of cosmic structure. His research focuses on addressing the measurement problem in the early universe, specifically investigating how transition from quantum symmetric state to an inhomogeneous classical universe occur during inflation. Professor Sudarsky's work often involves the application of objective collapse theories, such as the continuous spontaneous localization CSL model, to explain the birth of primordial fluctuations. His recent contributions explore the phenomenological consequences of energy momentum no conservation, proposing that such effects could provide a novel explanation for the nature of dark energy and the cosmological constant. Thank you very much, Professor, for accepting our invitation, and you have the word now.
Thank you, Giovanni, for the invitation. I'm very happy to share with you all this line of work on which we have been involved for many years now. The work I'm going to talk about is not one particular work; it's a series of work involving many colleagues. The latest ones are listed here, but there are many more colleagues that have participated in precursor works. All this line of research has taken over, for almost 20 years now, and has involved many colleagues and students. I take the opportunity to advertise the John Bell Institute is for the Foundations of Physics. Is a project in which we are trying to promote the teaching and development of foundational aspects of physics that we believe are not often considered sufficiently. And I invite you all, if you are interested, to look at the webpage of the John Bell Institute to see, our activities and things you may be interested in considering participating. Okay, so plan of the talk. First, I should warn people that I'm going to be talking about points that are often ignored, often dismissed, and I will be challenging some ideas that have been permeated through the community and that we believe need to be addressing. First, I will give you an overview of the general approach of treating the gravity quantum mechanics interface. In particular, I'm going to touch on the M problem and paths to address it, focusing in particular in these dynamical collapse theories, and I will briefly explain what these theories are about, and then I'm going to try to convey to you how we believe these ideas can be put together with semi-classical gravity, and I will explain why semi-classical gravity. And then I'm going to go to concrete applications of these ideas to inflation, in particular the seeds of structure, tensor modes, and eternal inflations, which are topics we have treated recently. All right. So first, let me say a word about methodology. We approach the exploration of this regime, the quantum gravity, the quantum theory, general relativity interface, in what we like to call a top-bottom approach. Top meaning the closer to the mundane experience, and bottom refers to a more fundamental theory. This approach is viewed in contrast with the standard way in which people address this question, which is what we call the bottom-up approach. The bottom-up approach postulates that one has on its hands the fundamental theory of quantum gravity, for example, string theory, loop quantum gravity, or any of the other paths that have been explored, and then works very hard trying to connect to the regimes of interest in the world out there, like cosmology, black holes, etc. Um, in our view, this is a very strong bet that you have in your hands the correct theory of quantum gravity. And then we prefer to take the opposite approach, which is taking existing and well tested and developed theories to address issues that seem to lie a little bit beyond their domain, considering possible modifications that can serve as clues about the more fundamental theory. In other words, we will not be thinking that what we are doing is the fundamental description, but is a step closer to a fundamental description based on uh, things that we believe and have very good reasons to trust. What is these things that we believe and have good reasons to trust? Well, the best theory we have to describe gravitation is general relativity. The best theory we have to describe matter is quantum field theory. And this brings us to the idea of putting these two things together, which is known as semi-classical gravity. Semi-classical gravity is therefore an approach in which you treat gravitation in classical terms and quantum mechanics and matter in terms of quantum field theory, without believing that this is the fundamental description. Okay, so let me touch on an example of things that are usually not, points that are usually not emphasized and not considered. And these are the issues. This example that I'm going to give you is one that plays an important role in cosmology. And the example refers to quantum uncertainties or indefiniteness that are often referred to as quantum fluctuations. And I am very concerned about this terminology because it provokes or it leads to confusion between these quantum fluctuations or quantum uncertainties and stochastic or even thermal fluctuations. These things are something very different. Those fluctuations, stochastic fluctuations, are small changes occurring in a system that occurring in time, for instance, or variations in localized aspects of an extended system. For example, the surface of a lake may have small variations from point to point, and these are normally described in terms of stochastic fluctuations. In general, these are variations among variations within a system in time or in space, or variations among individual systems. The fluctuation of the grades of students in a class. Every student has a definite value of his grade, but of course there is the average and then there is the dispersion to characterize the whole collection. Quantum mechanically, I'm going to argue that quantum mechanically we have something that sounds similar but is not similar at all, and we should pay attention to the difference between these two things. These ideas occur, or these fluctuations play a role an important role in our treatment of various cosmological issues. For example, the emergence of the seeds of cosmic structure, the generation of primordial gravity waves, and this fundamental problem that we are going to talk about, eternal inflation. So quantum uncertainties may justifiably be taken as measures of something stochastic, but this stochastic aspect is the result of having done a measurement on the system, which provides then the system, after the measurement, changes its state, and the resulting state and the resulting value of the quantity that we're measuring will vary from one occurrence to the other. So quantum mechanics is connected with stochastic results, but only in connection with an appropriate measurement. And this brings in the M problem, the measurement problem, into the discussion, which, as I said, is something that normally people do not like to discuss. From my point of view, the measurement problem, I like to call it the M problem, is a very, very serious problem, and ignoring it is just ignoring the elephant in the room. What is the problem? Let me, if you're not familiar with this, the problem is that quantum theory contains two laws of evolution. When you take a textbook in quantum mechanics, there are two laws of evolution. The U evolutionary process, which is basically the one dictated by the Schrodinger equation. This process is completely deterministic, reversible. The equations are reversible in time. One can go in one direction or the other. And then there is the reduction process, or connected with the reduction postulate, which is a different type of behavior that the system has when it's subjected to a measurement. However, this would be no problem if the theory was clear about what a measurement is, what circumstances constitute the measurement, what objects and things can be thought as playing a role of measurement device. And we believe we normally have a very good understanding of this and very good control, and this is not really a serious issue, but I'm going to show you that this is not the case. So let me illustrate a instance of the measurement problem, which hopefully will convince you that there is this problem. So this is connected with alpha decay, the study of alpha decay, studied by Mott in 1929. He wanted to understand how radioactive nuclei, assumed to be spherically symmetric, would decay, producing a particle that goes in one direction, even though the whole problem is, for instance, spherically symmetric. He thought he solved this problem, but he didn't, because he put in the solution part of the assumptions of what he wanted to solve. And I'm going to illustrate this with what we call the mini-Mott problem, which is a simplified version of this idea, considering now the problem in one dimension. So consider a particle, in one-dimensional free particle, which is prepared in a wave function or in a state that is symmetric between x and minus x. And there are two detectors, one located at position minus x0, the other one at the position plus x0. The whole situation is completely symmetric. As you can see in the graph, we can actually put everything in the explicitly. For instance, we can write the Hamiltonian for the particle, for the free particle is simply the non-relativistic Hamiltonian of a free particle, p squared over 2m. Then we can have each one of the detectors with energy E or minus E, epsilon or minus epsilon, depending on whether the detector is excited or not, and then an interaction Hamiltonian connecting each particle with each detector. Here we see that the Hamiltonian of particle 1 is connected with transforming the state that was excited to unexcited, and vice versa, if the particle is at the location where the detector is. So that's the delta function there. And we have a similar expression for the interacting with the other detector. And now we take the initial wave function, which is the two detectors are unexcited. This particle is in this, is characterized by, in terms of position, in terms of that state. And of course, the situation, as I described, was completely symmetric. In x goes to minus x, 1 goes to 2, and vice versa, right? Please, if there is some doubts, let me hear them. If you want to ask about things that clarify the discussion, please stop me. If you have something that is more involved and requires a long discussion, we may leave that for after the talk is done. Okay, so given that I have given you all the Hamiltonians, the Hamiltonian of the particle, the Hamiltonian of each one of the detectors, and the interaction Hamiltonian, and I can have given you the evolution, presumably everything is there for you to be able to tell me what will happen. And one can solve the Schrodinger equation in this case, basically almost in an exact form. And after some time, the evolution of the state would be written in the expression that I have put there, where we see that the first term corresponds to the detector one being excited, the second one corresponding to the second detector being excited. Then there is a third component in which both the detectors remain unexcited. No measurement detects a particle, so no detection occurs. And then there is a third term in which the two detectors get excited, which is a little less intuitive, but okay, that's a possibility that is a component that will appear as well. And one may think that looking at the first two terms, those terms characterize the possibility that the initial symmetry was broken, because in the first term, the state, one of the states, one of the detectors is excited, and in the second detector, and these two situations are not symmetric, and we think that we have really solved the problem. Everything seems fine, and the people will tell you, okay, this is what we do, and this produces the right result. However, we could have used, instead of the basis in which I describe the final state, I could have used this other basis. Let me call it the U, D, S, and A basis. U and D are the two situations that correspond to double detection, and D, well, here I mix up the letters. It should be, double detection should be the first line, undetection, no, non-detection should be the second line, and then there is a symmetric and an antisymmetric wave function. And of course, we could have written the final state in terms of that, on that line, and interpret those as the possible situations that would happen. And then you would say, well, all of the situations that occur were all symmetric, because even though, of course, the double detection is symmetric, the undetection is symmetric, and the first, this mixed detection in which the detectors are in this superposition of the first being excited and the second being excited with one particular phase, and with the opposite phase, the one that is associated with the antisymmetric is multiplied by an antisymmetric component of the wave function. Antisymmetric in x goes to minus x, and therefore the whole situation is symmetric. The point of this example is that we could have stayed with the conclusions of the first, but there is no reason why to trust those, in contrast, and not trust the conclusions of the second scheme. So in the second story, there is no component in which the symmetry is broken, while in the first, the symmetry was broken. In other words, we see that even though we have put the measurement devices into the analysis, we cannot tell you what of the things, the theory cannot tell me what of the things that are out there happens. Of course, we know that in the lab, the detectors are always found, the detector is either excited or not excited. So the states 5 and 6, we intuitively believe are not the right thing to consider. But this intuition doesn't come from the theory. This intuition comes from our own practice and our own experiences. But this is not reflected by the theory. There's nothing in the theory that tells you use the second scheme, or the first scheme versus the second scheme. In other words, we cannot account for how the symmetry is broken, even though we have put detectors into the full description of the system. Okay, so this is an illustration of the measurement problem. Okay, how do I go there? Oh, sorry. And it becomes much more serious in cosmology, because there is no even a candidate for an observer or measuring device that could be playing a role in the early universe. People sometimes decide it's best to simply ignore these conceptual difficulties and adopt a practical posture where one basically thinks that the quantum uncertainty, in this case, we could look at the quantum uncertainty in the full state of the system, indicates somehow that the system is jumping around from one of the various components that appear in the state. In the beginning, interprets quantum uncertainties as jumping around or things moving in time or something like that within the corresponding uncertainty range. Even though this is done very often, is completely unjustified, and it's also a very dangerous posture because it can lead you to be in conflict directly in conflict with experiments. One such example is one we precision measurements or precision searches for a non-vanishing value of the electric dipole moment of the neutron. So this is a quantity that people are interested for reasons of not found is that are, sorry, 10 to the minus 14, 10 to the minus 15 electron centimeters. These are if we view uncertainties as indicating that the system was jumping around within that range of values, it would be impossible to account for the fact that the bounds that are currently obtained on this quantity are at least 10 orders of magnitude tighter than the quantum uncertainty. So we are making now measurements producing that are 10 orders of magnitude more precise than the quantum uncertainties. Quantum uncertainties, if they were thought as the system jumping around with shut up and compute posture is simply untenable in view of experiments. If you want to read more about this particular experiment, we have a paper published here. Now is now part and part of the standard of
Hello. Daniel, can you hear me?
hello.
Yes, Daniel.
Hola.
Hola.
Yep. Hola. Hello.
Yes, yes. Can you check
Please.
again, please, your slides?
Okay. I need to share again this slide. Sorry. Yeah, I don't know what happened.
Yes, I don't know. I had the connection.
Okay. Sorry, everybody is with me. Is
Yes,
there any Are there any questions so far?
not
No?
yet.
Okay, good. Okay, so I hope everybody is familiar with the basic ideas of inflation. To be concrete, we can think of a very simple inflationary model with just one scalar field and a simple potential, which for concreteness, I may choose it to be the one using so-called chaotic inflation, I don't know what the name, which is simply a quadratic potential on the field. And looking at the action, we see that the potential, if it was constant, it would basically act as a cosmological constant, and that's what happens during inflation. Basically, the fields are taken to be changing very slowly, and therefore, the first term is basically negligible, and then we have a situation in which the universe should be behaving like one dominated by a positive cosmological constant would mean the universe would be expanding in an accelerated way. The idea of inflation is that this dynamics drives the universe into an extremely homogeneous and isotropic state in which all matter components, including defects from earlier phase transitions, are exponentially diluted, and this solves this particular problem and other naturalness problems like the horizon and flatness problem. But the biggest success of inflation is that it's supposed to account for the emergence of the seeds of cosmic structure as precisely as the result of quantum fluctuations. And if one does the calculations in the way that they are prescribed, one obtains results that seem to match very well with the observations. However, at the conceptual level, the account is simply not satisfactory because it precisely makes use of this identification of quantum fluctuations as if they were stochastic fluctuations, which we saw are just untenable. So to be a little bit more concrete and specific, let me describe how the treatment go, and I will focus on where the issues arise. One starts by considering a completely homogeneous and isotropic spacetime, on top of which one introduces perturbations. In this case, these perturbations are characterized by what is called the Newtonian potential, appearing in the first equation in terms of with the letter phi, reflecting the part of the metric that in principle could contain inhomogeneities and anisotropies. And then there is Hij, the tensor perturbations that are also places where inhomogeneities may be present. The matter is represented by the inflaton field, which is described in terms of a part that is homogeneous in space and may depend only on cosmic time, or here conformal time, and a perturbation delta phi. So we have this set of perturbations: delta phi, the Newtonian potential, the tensor components, and these are the places where spatial dependencies may or may not may occur, but of course these quantities may be zero. The background is supposed to be treated classically, and is assumed to be dominated by the inflaton potential in a particular condition called the slow roll regime, so that the potential changes, so that the field changes very slowly with the cosmic time, and then the scale factor of the universe, A, then behaves approximately in the way that I described. And then the perturbations are treated quantum mechanically and assumed to be characterized by something called the adiabatic or Bunch-Davies vacuum state, simply because, again, inflation was supposed to dilute all pre-existing features and drives the state, all fields toward the vacuum state. But the state is also, this particular state, this Bunch-Davies state, is also characterized by the so-called quantum fluctuations or uncertainties of these quantities. And here we face precisely this kind of confusion. In these usual treatments, then one computes, after computing these quantum uncertainties, one identifies them as if they were stochastic fluctuations and identifies them as the primordial, as the source of primordial inhomogeneities in the universe, uh, which lead, of course, to the formation of uh, structure, galaxies, planets, etc., and eventually us. And these are thought to have left their first traces in the CMB, and as I said, the results are extremely well fit can be very well fit to the observations. But as I said, to emphasize again, that situation is completely homogeneous and isotropic, both in the part that is described in classical terms, the background, and the part that is described in quantum terms. The state is the Bunch-Davies vacuum, and that state is 100% homogeneous and isotropic. If that is the correct description of the universe at that stage, then the question is, how does the dynamics of a closed system, which the universe is a closed system, break these symmetries if the dynamics is not able to do it? So this is an instance again of the M problem. If we had a measurement, we perhaps could argue something along these lines. People nevertheless have deployed all sorts of arguments to justify that step. Arguments that appear often in the literature involve decoherence, squeezing of the vacuum, reduce uncertainties, as indicating these are somehow justifiably this would justify a use of a classical description or something of that sort. Well, we have discussed this in various papers, but I think a very clear statement concerning all this is that if we take classical theory to supervene on quantum theory, meaning that the quantum theory is the more fundamental description and the classical description is only an approximated description that should be deduced on the previous, then a symmetry cannot be broken at the classical level in the state if it's not broken at the quantum level. In other words, you cannot have a situation in which the more precise theory tells you the situation is symmetric and the less precise theory tells you that the situation doesn't have that symmetry. That is simply logically impossible for for any theory in which you have any pair of theories that are related by this fact that one is more fundamental than the other. People have argued, trying to argue, for instance, that spontaneous symmetry breaking can play a role. We have investigated and this possibility. We have shown that this is not what's going on. If you want to look at that result, this is published in that paper listed at the end. Okay, and here we have a pictorial diagram of what we think cannot be. It cannot be either. Here we have a Schrodinger considering, a pool that is perfectly smooth, has a perfectly smooth surface, and then he looks at the pool, and by looking at it, makes it rough. And this is if we took this view that our looking at the universe is what breaks the symmetry, we have a very serious conceptual problem, because of course it means that we are the cause of the emergence of galaxies, which of course are the prerequisite for our own existence. So we will be causing our own existence by our observations today in a closed circle of explanatory attempt to explanatory, which of course doesn't work at all. Okay, a good framework to consider this and other aspects of the measurement problem is the following result by Tim Modlin, which serves to, in our view, to characterize very clearly what are your options regarding the measurement problem. And the the result of modeling shows that the following three premises cannot be consistently uh, defended or sustained at the same time. You cannot simultaneously hold on to the following three statements, meaning that you have to give up one. So the first statement is the characterization of a system by its wave function is complete. Negating that statement means that you go to a system in which you have something more than the quantum state is required to describe the system, and then you have to go into the direction of hidden variables or something of that sort. The second premise is the evolution of the wave function always follows the Schrodinger equation. Its its negation leads, for instance, to, let's say, textbook approaches to quantum mechanics, in which you say, upon observation, things change, or spontaneous collapse theories, which we think is a version of this idea that is much more uh, serious and precise and viable of uh, being considered as a serious candidate for a theory. Third, experiments lead to definite results. It, it does not mean that if you do an experiment, you can predict it, but that if you do an experiment, you will obtain a definite result. I prepare a particle direction, this thing, and I measure it in the y direction, and the results plus. So one particular experiment will produce one particular result. If you want to negate this premise, you go into the realm of many world interpretations or things like that, in which one experiment produces, in some sense, all the possible of. So here, what I'm showing you is that you have no easy way out of this problem. You have to get rid of at least one of the premises, and they all are involve departures setting. If you want to admit the three premises, you have a very serious problem, because by admitting these three premises, you get into contradictions, and when you get into contradictions, you cannot trust anything you conclude. Okay, so I'm going to go into the direction that we think is most promising, which is negating the second premise. And the negation, we will do it not in the way Copenhagen or in the way textbooks do it, because, as I show, those approaches are not sufficient to deal with the cosmological situation we have at hand, where we can find no measuring device, nothing analogous to the detectors or anything of that sort. So this is the path called spontaneous collapse theories or collapse theories. And what single evolutionamics, the two types of evolutionary process that appear in quantum mechanics, the evolution according to the Schrodinger equation and the uh, collapse postulate. But now the collapse is not occurring because somebody makes a measurement. It's occurring spontaneously in all at all places and at all times as part of the intrinsic laws of nature. So one particular, well, these lines of work have been explored for several decades now, starting in the 80s. And here are, of course, important names in that regard, including Penrose, that consider, together with Lajos Diossi, consider tying them to gravity. Anyway, let me give you one particular example of this type of theories. It's called the CSL theory. It's one of the most evolved versions of the theory. The theory is characterized by two equations. One equation that is the modified evolution equation, which is given by equation 8. If you look at the first part, we have exponential, well, time order product of the exponential of the Hamiltonian, the standard Schrodinger part, and then there is a correction term appearing in the second term that contains three objects that I'm going to describe briefly. One of them is the collapse rate, the lambda parameter there. The other thing is the collapse operator that tells you towards which type of states the system tends to be driven by the spontaneous collapse. And in this case, these are eigenstates of the operator A. And then there is a stochastic function of time, which encode reflects the stochastic nature that we believe is present in quantum mechanics, and which in normal descriptions is hidden in the way we use the reduction postulate. Here we have an explicit expression for this stochasticity appearing in that form. So this is a random classical function of time with white noise. And then we have, since the evolution is no longer unitary, you don't compute probabilities in the standard way. What you compute is the probability of the realization of a particular version of this stochastic function, and that probability is written by equation number 9. Let me not get into the details. And then for what is taken to be the collapse operator, it's in non-relativistic quantum mechanics is taken to be the position operator smeared over a scale. So it's not precisely the position operator, but it's a position operator smeared over the scale of a certain scale, which is taken to be one of the parameters of the theory, thought to be of the order of 10 to the minus 5 centimeters. The theory is designed to explain why, when you make a measurement with an apparatus that contains many particles and that becomes entangled with the object that you are measuring, you obtain a result. Basically, here the result would come out by forcing the apparatus to be in an eigenstate or very close to an eigenstate in the pointer of the apparatus pointing in one particular direction. Okay, the theory is being tested experimentally. People are doing also many experiments, and various regions of the parameter space have been, have been disallowed. But of course, there remains a relatively large area that is still viable. The idea of the theory is that this parameter of characterizing the collapse of a particle should be a very, very light effect in systems with very few degrees of freedom, and it would become important when you have many degrees of freedoms entangled. So, for instance, the parameter should be small enough that the particle, one single particle, is not affected if it's isolated, and then it's taken to be something of the order of 10 to the minus 17 seconds to the minus 1. And that means a single particle will spontaneously collapse to something like close to an approximated position eigenstate in the age, something like the age of the universe. But when you have 10 to the 32 particles, all of them entangled, it's enough that one of them suffers a collapse, and then the whole system becomes something close to an eigenstate of the position operator, of the collective position operator of the whole thing. So this happens very quickly for relatively large systems. These theories containing this stochastic aspect implicitly, and by stating that this stochasticity is occurring all time, regardless of whether there is a measurement or not, are able to break down the symmetries, and therefore we consider incorporating them into the inflationary cosmology picture to address the problem we have noted, right? The problem of how does the symmetry break in the early universe if there is nobody to measure it. So these theories contain a modified evolution, space-time evolution of a quantum system. In the case of non-relativistic quantum mechanics, it was a modified time evolution. In the case of quantum field theory, it will be modified space theory. tells us to go to a treatment in which we in the in curved space-time. So that is the reason we are led to use semi-classical gravity. However, semi-classical gravity itself is a theory that on the one hand cannot be considered fundamental, or it's difficult to consider it fundamental. There are discussions, but even if it's considered, doesn't matter how it's considered, problems. For instance, they supposedly describe an experiment in which we try to put an object, a relative mesoscopic object, in a quantum superposition of being in two places, and then try to detect the gravitational field that it creates. So they look for the gravitational field of a system in a superposition of two locations, and from doing the analysis of their thought experiment, well, almost thought, but have done. Let me not get into the details of the experiment. If you want, you can ask me later. They conclude the following: if there is a collapse of the quantum state, the theory, if there is no collapse of the quantum state, the theory is in conflict with evidence. Basically, the point was that the situation was symmetric, and then you shouldn't find a deflection of your needle in any one of the directions. What they saw is a deflection in one direction, so that's contrary to the prediction of no deflection is contrary to experimental evidence. And on the other hand, if there is a collapse of the wave function then the theory is simply inconsistent, they claim. And the last statement is based on the observation that during a collapse, the expectation value of the energy momentum tensor would have to change in a discontinuous way, or jump in one way or the other, and that is in conflict with the semi-classical Einstein equations, simply because in those equations one identifies the Einstein tensor with the expectation value of the energy momentum tensor. The Einstein tensor automatically satisfied due to the Bianchi identities, divergence equal to zero, while the right-hand side, which is the expectation value of the energy momentum tensor, doesn't satisfy that condition during a collapse. Okay, so this is a difficulty that needs to be dealt with, and I'm going to explain briefly how we think of getting rid of it. But before doing that, let me tell you the following. We have this result in that paper with Tim Modlin and my colleague Elias Ocon. And we have argued that all reasonable paths, that is, all the three paths that I described for dealing with the measurement problem, lead to the same problem of energy momentum non-conservation. So we think that all solutions to the measurement problem involve non-conservation of energy momentum tensor. So this problem is something that you will face no matter how you try to deal with the measurement problem. This tells us that we cannot think of semi-classical gravity with any resolution of the measurement problem as a fundamental theory characterizing the interface of the quantum and geometrical aspect of natures. But we can view semi-classical gravity together with a suitably adapted spontaneous collapse theory as an approximate description. What do I mean here? Consider hydrodynamics. Consider the Navier-Stokes equations. Those equations are very elegant, very nice. We have all sorts of theorems of how to solve them, and they serve to describe the behavior of fluids in many, many situations. But of course, there are situations in which this theory, not being fundamental, will break down. For instance, take the surface of a lake. You may imagine describing that using the Navier-Stokes equations. But if there is a wave forming and the wave forms a cusp and then starts breaking in the beach, forming foam and all sorts of things, during that process, the Navier-Stokes equation is not going to be valid. It's going to break down because the Navier-Stokes equations do not reflect the fundamental degrees of freedom, which is the molecular and atomic degrees of freedom characterizing the fundamental description of the fluid. However, after the wave has broken down and gone to the beach and became smooth again, and the foam goes away, when the wave starts receding from the beach, you again have conditions where you can use hydrodynamics to treat the situation. So we will look at spontaneous collapse as being something like that. The theory will be valid while when the collapses are not going on, and the collapse will be a situation in which the theory breaks down. Then, if you want to have a description, you have to find a reasonable way to join the two descriptions, the description before and after. So the idea is that the theory would be valid when in regions where no collapses have happened, and and I'll describe how to treat it when they do happen. So to make things more explicit and precise, let me first describe how to describe the physical situation, or what would be the precise description that we would be taken to in which the theory of semiclassical gravity is valid. So we incorporate this notion of semiclassical self-consistent configuration. So what is this? This is basically a space-time together with a quantum field theory constructed over that space-time. So means the phi and is the field, pi is the momentum conjugate, h is the Hilbert space on which these fields are acting on as operators. And then there is one particular state in the Hilbert space that is going to be called the physical state. All of this satisfying the following requirement. First of all, the quantum field theory satisfies the Klein-Gordon equation in the background in the space-time, and so that's what it means to construct a quantum field theory over that space-time. And then the state is such that the expectation value of the energy momentum tensor of the field operators renormalized is equal to the Einstein tensor for that metric. So this is a fully self-consistent and self-referential frame, because as you see, the quantum field theory, including the Hilbert space, requires the space-time to be constructed, and the space-time is required to be connected to the quantum field theory construction, and in particular to that state, through the Einstein equation. So the two things need to be, self-consistently. The whole construction needs this self-consistency and self-referential aspect. So this is the general relativistic version of something called the Schrödinger-Newton system, which is a non-relativistic version of this proposed by Lajos-Diósil many years ago. Okay, so this is the description of the system while the theory, while there are no collapses. When there is a collapse, the state of the field changes spontaneously. If the state changes, the expectation value of the energy momentum tensor generically changes, and therefore the space-time metric needs to change, and then the whole construction of the quantum field theory needs to be changed, and therefore this whole self-consistent configuration needs to be changed for another one in which we replace the space-time, replace the quantum field theory construction, and replace the physical state. So a collapse would be described by one self-consistent configuration transforming into another one. Okay, so it's in this setting, the collapse produces not only a change in the quantum state of the field, but also a change in the space-time metric. Doing this is mathematically relatively complex. In this paper, we have done it in very, very minute detail. You can follow it. but in general, now expanding the this setting and expanding the collapse theory to the relativistic quantum field theory regime is highly non-trivial, and I'm going to mention a few issues that appear and that we have managed to somehow deal with some of them. The general construction of the collapse of the second self-consistent configuration from the first one, given the collapse, requires requires dealing with delicate issues. In particular, the renormalization problem becomes very, very subtle, and this was explored in this paper with Benito Juarez and Bernard Kay and Tonatiuh Miramontes. So we think we have this under control. Another issue is that the modification of the theory by incorporating spontaneous collapses may revive or bring back the possibility of faster than light, of your theory predicting faster than light communication. We strive to avoid that. We have shown that this problem appears even in more mundane settings. For instance, there is this famous paper by Wald and Unruh called "What Happens when a Rindler detector detects a particle." We have written a paper that explores further issues that have not been considered there, in particular, the renormalized energy momentum tensor in regions outside the domain of communications of the region where the accelerated detector is, and seen that in principle this can produce faster than light communication. But we have found a way to solve the problem, determining that the state that needs to be used in computing the expectation value of the normalized energy momentum tensor should be the state associated with the past light cone of the point in question, and that seems to deal with the problem. Then there are issues like the issue of quantum uncertainties in the energy momentum tensor. For a long time, this was something that was thought that not be possible to compute, to be impossible to compute, due to the fact that the calculation produces state-dependent divergent quantities, which are therefore not suitable for renormalization in the standard way. We have found a way to deal with this using something called the operator power expansion in this paper that is still being reviewed, but if I can find it in the archives. So all these issues are issues that need to be treated if you want to follow this scheme. Let me now tell you what happens when you apply these ideas to the inflationary setting. So when we apply this to inflation, we follow the recipe that indicates all matter fields should be treated quantum mechanically, and therefore that refers also to the to the zero mode of the field, not only the perturbations, but the whole thing. The quantum state of the scalar field then is supposed to be connected with the gravity in this form, and then through the semi-classical Einstein equations, and using that one obtains basically the standard result for the behavior of the background, in particular the standard inflationary expansion rate for the scale factor of the universe. However, the interesting things will occur when we look at modes that are not the zero mode, the modes that have a given wavelength, finite wavelength, characterized by the wave number k. We have studied what happens to this system when we assume that each one of the modes of the field undergoes a collapse, and using a natural gluing recipe for this SSC formalism. Natural gluing means describing the second configuration results from the first. Uh, Basically, we have found shortcuts that are produce basically the same results than the more complicated and rigorous formalism, at least when we study things to in the lowest order, lowest orders in perturbation theory. In this situation, basically, we have the operators corresponding characterizing the mode K, which are the field operators and the momentum conjugate to the field in the mode for the mode K. And for these operators, we have in the ground states, they are described, they are characterized by Gaussian wave functions that are centered around zero and with certain uncertainties. And the background, and the perturbations of the metric are vanishing. Therefore, the space-time is homogeneous and isotropic. The state is, as I said, homogeneous and isotropic. However, when a collapse occurs, the quantum state would change, and the expectation values of the momentum and field operators in decade mode will acquire values that are not the vacuum values, but some other values due to the stochastic aspect of the collapse. And if we assume that the collapse occurred mode by mode and is described by an adapted version of the collapse theory, uh, and remembering that our universe would correspond to one particular realization of the collapse or the stochastic function for each one of the modes, we can uh, look at the part of the Einstein equations that controls for instance, the Newtonian potential in the metric. And for that, going to the Fourier transform of that and focusing on a particular mode, the Einstein equations takes the form 11. And I want to point you to one important aspect of this. If we consider the state of the field was the vacuum, the expectation value of the momentum conjugate would be zero, and therefore the Newtonian potential would be zero, and their spacetime would be homogeneous and isotropic. And this is perfectly consistent with what we know. If the state of the field is homogeneous and isotropic, the spacetime should as well be homogeneous and isotropic. However, if the collapse has changed during the collapse, this quantity changes and becomes non-zero, then the Newtonian potential becomes non-zero, the spacetime stops being homogeneous and isotropic, and we have creation of inhomogeneities. So the inhomogeneities are created as a result of the spontaneous collapse and not as in the usual scheme interpreted as if the quantum fluctuations represented stochastic fluctuations. If we do this, if we follow this analysis, requires a little bit of calculations, and we take, for instance, the operators to be collapse, the momentum conjugate, or the momentum or the field operator, and take the values of the collapse parameters to be the natural form of the bidimensional consideration that they take by dimensional considerations, we get the prediction for the spectrum, which coincides with the standard prediction, which is equation 12. We know that this produces the scale invariant the spectrum that, when it's modified by the late plasma dynamics, produces the correct uh, uh, spectrum of primordial perturbations that we do see in the CMB and that are reflected in the large scale distribution of matter in the universe. If we set the parameters of the theory to be basically GAT scale, we would obtain the value of the parameter of the fixing the spectrum to the observation will give us the value of the collapse parameter, and it turns out to be of the order of 10 to the minus 19 seconds, which is not very different from the GRW suggestion that we encounter in the context of non-relativistic particle mechanics. But of course, these two theories need to still be connected. Other possibilities for collapse operators have been explored and give different results. Let me not get into that. So this is the first thing that we are happy about. We have now an account that does explain how inhomogeneities arise in the universe and produces the correct spectrum for these inhomogeneities. But if we go to the tensor modes, the Einstein equations for the tensor modes take the form of equation 13, where you see that the result, the left-hand side of the equation 13, is quadratic in the collapsing quantities instead of being linear. And this, I mean, after doing some calculation, this leads to a spectrum for the primordial uh, uh, tensor perturbations, which is given by equation 16, which should be compared to the one that I gave you previously for the scalar perturbations that I repeat there in equation 17. And you see two different, very important differences. First of all, the potential, the inflationary potential divided by the Planck scale appears quadratic in equation 16 in contrast with the linear occurrence in the equation 17, and this is due to the fact that the theory is quadratic in the collapsing that the tensor modes the source is quadratic in the collapsing quantities instead of being linear as in the previous uh, case. And this is a very different prediction from the standard calculations for the tensor modes, which this means is that the prediction from this approach is that tensor modes are not expected to be seen at the level they are being sought for or they are being looked at, in contrast with most models of inflation in which you predict that the tensor modes should have already been seen. In fact, uh, we can put a graph of what is the spectrum and compare the standard prediction of the spectrum, which is the red line, which for most models, as I said, indicate that we should have seen these tensor modes, and we have not seen them. The prediction from the approach I have just described are well, we have two predictions depending on the collapse theory we use, but they are both extremely suppressed compared to the first. In particular, is almost 8 orders of magnitude below the scheme, and it means that we should not see the predictions. Both of these approaches is we should not see these tensor modes at the level we are looking for, which of course it goes with observation. So this is a very different prediction, which illustrates also that the approach has not only philosophical interest but actual, concrete physical predictions that differ from the usual approach. Finally, let me see how are we doing on time. I'm probably running late on time. How am I doing, Giovanni? Okay.
I think we have plenty of time.
Okay, so let me go then to the final topic connected to the inflation, which is the problem of eternal inflation. This is supposed to be one of the most serious problems afflicting the inflationary paradigm, so serious that some people that were actually among the proponents of the inflationary ideas have now given up on inflation due to this problem. And the argument of the problem is the following. Inflation is the following. Inflation is driven by the inflaton zero mode, or the mode that is homogeneous and isotropic, whose value determines the value of the potential that appears as an effective cosmological constant, as I remarked at the beginning. And this mode is has a classical displacement as it rolls down the potential, but it's argued that quantum fluctuations should also affect this field, and that these quantum fluctuations, if they are larger than the classical displacement for a characteristic time, may dominate over the classical displacement. So the potential, the inflaton is going down the potential due to the slow rolling, but is now supposed to either go stochastically up or down depending on the quantum fluctuations. Here again, look at the argument. We are taking quantum fluctuations as if they were stochastic fluctuations. But if we do that, then the argument goes like if the quantum fluctuations are larger than the classical displacement, then the field will go up in some regions and down in some other regions. When it goes up, it will increase the value of the cosmological constant, so that region will grow faster. When it goes down, it will decrease the value of the cosmological constant, so that region will grow slower, and the universe will then be dominated. Most of the volume of the universe will be occupied by the regions in which the potential went up, because those regions grew faster, and therefore over time the universe will be dominated by regions in which the potential move increased, and this means that inflation, instead of stopping, will never stop and will continue going forever, and this is the problem of eternal inflation. Okay, so it comes from a comparison of the quantum fluctuations, which, as I said, are quantum uncertainties, with the classical displacement, and the interpretation of these fluctuations as if they were stochastic fluctuations, which, as I said, is a mistake. No, so once again, this argument relies on the incorrect interpretation. And moreover, another part of this bothersome is that the inflaton zero mode is completely homogeneous and isotropic, so it cannot go up in one place and down in some other place. If it goes up, will go up in the whole universe, so the story also has a problem there. But the part that I want to concentrate on is the fact that there are quantum fluctuations cannot be interpreted as stochastic fluctuations. However, as we have seen, we have to deal with the problem of emergence of structure, we have to introduce a stochastic aspect in the theory. This stochastic functions that control the collapse dynamics. And it could be that this stochasticity, now changing the expectation values of the various field operators, produce something similar to a stochastic type of noise that would really bring back the inflationary setting. So in this case, we need to if we want to study that, we have to study it, but not simply compute the quantum uncertainty of the field, but we have to compute the actual stochastic variations that are induced by the collapse theory in the expectation values of the fields. So we need to compute the classical displacement in a characteristic time with the stochastic mean of the displacement due to the collapses, which is slightly different from the previous situation, which I explained, it doesn't make sense. If we take the implementation in which the implementation of the collapse theory, in which the field operator is the one that undergoes collapse, or in other words, we take the collapse operator to be the field operator, then we saw that the rate of collapse is controlled by this expression. Is lambda or lambda tilde is a constant, so it's proportional to k, and therefore the mode k equal to 0 is not subject to collapse, and therefore it seems that the eternal inflationary problem would not be present. This, however, is a little bit simplistic, because we have to confront the fact that there are modes that have such a long wave. They don't have k equal to 0, but they have k sufficiently small, and they are sufficiently large wave that they effectively act as zero modes, as the zero mode of the inflaton. And those are the wavelengths that are larger than, let's say, the particle horizon. So for those modes, we have to compute the stochastic, the contribution to the stochasticity on the mean value of the field in the mode K and consider all those modes that are larger than the particle horizon, and compare that with the classical displacement. It turns out that this does not work for the precise form that I gave you before for lambda having this particular dependence on K, but a slightly modified value form for the collapse that reproduces the correct behavior in the region where we see where the relevant modes for structure are seen and are detected, and modifies slightly the collapse rate at very, very long wavelengths. This scheme opens the door for solving the eternal inflationary problem while consistently reproducing the observations for the scalar modes. So the paper in which this is described is this paper with my former student, Rosa Laura Lechuga. And here we see a region in parameter space where the mark yellow, the region where eternal inflation is avoided. We have done a more precise analysis of this model, comparing it with the precise with actual data from Planck and other surveys, and found out that this region is confirmed to be a solution of the eternal inflation problem while reproducing, being successfully in predicting the observations. Okay, this approach offers paths to address other interesting problems and that have been bothering people for a long time, like the black hole information puzzle. Here I have some citations for papers connecting to that, and even the problem of timing canonical approaches to quantum gravity. Here is the paper we have discussed this issue, and as you can imagine, there is a lot of work remains to be done in exploring this line of approach. But I hope I have convinced you that the questions that are being considered here are both interesting and potentially extremely rewarding regarding solution of both conceptual problems and actual problems that are considered actual conflicts with observations like that of the tensor modes and eternal inflation. So thank you very much.
Thank you very much, Professor Daniel. Thank you for your very nice seminar. Are there any questions from the students?
Not everybody at the same time, please.
Yes, can be in Spanish, English.
Yeah, can be in Spanish.
Professor, yes, really the topic is a very complex topic. Yes, but could you please explain again what fixes the post-collapse semi-classical self-consistent configuration after the collapse?
Okay. So I didn't really get too much into the details, but the idea is the collapse theory tells us how the state would change. It does so stochastically, but once the stochastic function is chosen, it tells us in which state it will change. Now I have to construct a spacetime that is compatible with this state and actually construct the quantum field theory in that spacetime that contains something that is similar, that represents that state. Because as I said, the theory of collapse tells me that the state would change from this state to this other state, but normally it does so within the same Hilbert space of the in which we were working. So it tells me Maintaining your Hilbert space, it changes from this Hilbert space to this other Hilbert space. What we do in this construction is to construct a new state that has the same expectation value of the energy momentum tensor as the state to which the theory of collapse tells me I would collapse. So again, I first compute the new state in the old field quantum field theory, compute the expectation value of the energy momentum tensor, and compute a new state and design a new state in the space-time that I'm going to still construct, who has the property that on the initial hypersurface, it has the same expectation value as the previous, sorry, on the collapse hypersurface. Moreover, so this is the gluing recipe, what you are asking for. Moreover, I will require that the metric, the induced metric on the collapse hypersurface from below and from above are the same. So I will require a sort of continuity of the metric, even though I will not require continuity of the derivative, of the normal derivative of the metric. So the extrinsic curvature will undergo a spontaneous jump during the collapse. All this has to be done, and at the same time deal with the renormalization issue, because the energy momentum tensor is a complicated object that requires renormalization. So this is what is described in that paper that I mentioned, but I didn't really get into all the details of how to describe it. Although, I hope I have answered your question. Did I answer your question?
Yeah, yes. Thank you, Daniel. Yes, thank you very much. Any other question?
But let me reinforce. Your question is actually complicated question,
Yeah.
and this whole paper that I mentioned there is devoted to precisely deal with
Yes,
that.
and also how the metric is calculated, is determined.
Okay,
The
the
new
metric.
metric.
You see, again, before the metric, before the collapse, the metric is supposed to satisfy the Einstein equations. So if you have initial value formulation and it satisfies the Einstein equations with the expectation value of the energy momentum tensor, you know what it satisfies. After the collapse, it also will satisfy the Einstein equations with the new state.
Yeah.
Okay, and the initial data is going to be fixed by the requirement that the constraints are satisfied in both the previous, well, in the new construction, the standard constraints, and by the requirement of continuity of the induced metric on the collapse hypersurface. Those conditions, which we argued in this paper, that will result in a complete determination of the okay, these papers here, okay, Jacob 23, 24. In those papers, we have described this issue in detail, because all this issue becomes complicated by the fact that energy momentum tensor needs renormalizing while you are constructing. So you are constructing the space-time and renormalizing at the same time. And this is not trivial, because renormalization process uses features of the space-time.
Okay.
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 But
Thank you.
basically is Einstein's equations plus initial conditions will
Okay.
determine the spacetime afterwards.
Okay. Thank you, Professor. Any other question?
Yes, Professor, I have a question. I'm just asking that when you are designing the new Hilbert space from the previous Hilbert space, okay, you are taking the induced metric and everything. Now, are you considering the topology also of the space we are considering? I mean,
Okay, we are assuming that for simplicity at the moment, we are assuming that the collapse does not change the topology. Even more than that, as I said, we will require the induced metric on the space-time to be the same. I mean, on the collapse surface. So we have a space-time that goes up to the collapse surface, a space-time that goes beyond the collapse surface, and in that gluing, we demanded that the induced surface, induced metric on the surface from above and from below is the same. Not the extrinsic curvature. Right? We allow the extrinsic curvature to jump because
Yes.
we need to allow it, because otherwise we will not satisfy the constraints. Okay?
Thank you. Thank you.
You're welcome.
Okay, thank you, Ranil. Okay, yes, I think there are no any more questions. Perhaps, Professor, can the students and other colleagues write you if they have some question, or could be
Sure, they
possible?
can.
Yes.
Sure. No problem.
Okay. And then thank you, Professor. Yes, we can. I think we can close the seminar today. Thank you very
Okay.
much to you. Yes. Bye bye. Thank
Bye.
you.
Thank you.
Thank you, Professor.
Bye.
Thank you, Professor.
Thank you. Bye. Take care.